Learning objectives. In this chapter, the user would learn the following in detail: relational versus object-oriented database systems, semantic database systems, object hierarchies, generalization, specialization, aggregation, ER model, RM given T, SDM, SAM, Daplex, IFO, the architecture of object-oriented databases, query languages for object-oriented databases, Gemstone, O2, Orion Object Stone, Object Relational Database, Management System, Object Relational Database Management System, Oracle 8i, 9i, DB2. Overview of Object Database Systems, Object Relational Database Management Systems, Implementation and Challenges, a database design for an Object Relational Database Management System, Object Oriented Database Management System, a ODMG data model, and ODL. Comparison of Relational Database Management System, Object Oriented Database Management System, and Object Relational Database Management System. Introduction. Object Oriented Database Systems are proposed as an alternative to relational systems and are aimed at application domains. The approach is heavily influenced by object-oriented programming languages and can be understood as an attempt to add database management system functionally to a programming language environment. The Object Database Management Group ODMG has developed a standard object data model ODM and object query language OQL, which are the equivalent of the SQL standard for relational database systems. Comparison of RDBMS, OODBMS and ORDBMS. Comparing RDBMS, OODBMS and ORDBMS. Now that we have covered the main object-oriented database management system extensions, it is time to consider the two main variants of object databases: object-oriented database management system and object relational database management systems, and compare them with the relational database management systems. Although we presented the concept underlying object databases, we still need to define the term OODBMS and ORDBMS. An OODBMS is a programming language with a type system that supports the features discussed in this chapter and allows any data object to be persistent, that is, to survive across different program executions. Many current systems conform to neither definition entirely but are much closer to one or the other and can be classified accordingly. RDBMS versus ORDBMS. Comparing an RDBMS with an ORDBMS is straightforward. An RDBMS does not support the extensions discussed in this chapter. The resulting simplicity of the data model makes it easier to optimize queries for efficient execution. For example, a relational system is also easier to use because there are fewer features to master. On the other hand, it is less versatile than an ORDBMS. OODBMS versus ORDBMS. Similarities. OODBMS and ORDBMS both supports user-defined ADTs, structure types, object identity and reference types, and inheritance. Both support a query language for manipulating collection types. ORDBMS support an extended form of SQL and OODBMS support ODL given OQL. ORDBMS try to add OODBMS features to an RDBMS, and OODBMS in turn have developed query languages based on relational query languages. Both OODBMS and ORDBMS provide DBMS functionality such as concurrency, control and recovery. OODBMS versus ORDBMS. Differences. The fundamental difference is really a philosophy that is carried all the way through OODBMS try to add DBMS functionally to programming language, where OODBMS try to add richer data types to a relational DBMS. Although the two kinds of object databases are converging in terms of functionality, this difference in their underlying philosophy has important consequences in terms of the issues emphasized in the design of these DBMS and efficiency with which various features are supported. As the following comparison indicates, OODBMS aim to achieve seamless integration with a programming language such as C++, Java or Smalltalk. Such integration is not an important goal for an OODBMS. SQL 1999 like SQL 92 allows us to embed the SQL commands in a host language, but the interface is very evident to the SQL programmer. An OODBMS is aimed at applications where an object-centric viewpoint is appropriate, that is, typical user sessions consist of retrieving a few objects and working on them for long periods with related objects fetched occasionally. Objects may be extremely large and may have to be fetched in pieces. Therefore, attention must be paid to buffering parts of objects. It is expected that most applications can cache the objects that recur in memory once the objects are retrieved from disk. Therefore, considerable attention is paid to making references to ill memory objects efficient. Transactions are likely to be of very long duration, and holding locks until the end of a transaction may lead to poor performance. Therefore, alternatives to two-phase locking must be used. And OODBMS is optimized for applications in which large data collections are the focus, even though objects may have rich structure and be fairly large. It is expected that applications will retrieve data from disk extensively, and optimizing disk access is still the main concern for efficient execution. Transactions are assumed to be relatively short, and traditional OODBMS techniques are typically used for concurrency control and recovery. The query facilities of OQL are not supported efficiently in most OODBMS, whereas the query facilities are the centerpiece of an OODBMS. To some extent, this situation is a result of different concentrations of effort in the development of the systems. To a significant extent, it is also a consequence of the systems being optimized for very different kinds of applications. Database design for an object relational database management system. The rich variety of data types in object relational database management system offers a database designer many opportunities for a more natural or efficient design. Collection types and ADTs. Our first example involves several space probes, each of which continuously records a video. A single video stream is associated with each probe, and while this stream was connected over a certain period, we assume that it is now a complete object associated with the probe. During the time period over which the video was collected, the probe's location was periodically recorded. The information associated with the probe has three parts. Number 1, a probe ID that identifies a probe uniquely. Number 2, a video stream, and number 3, a location sequence of time location pairs. What kind of a database schema should be used to store this information? An relational database management system database design. In an relational database management system, we must store each video stream as a blob and each location sequence as tuples in a table. A possible relational database design follows. There is a single table, canned probes, and it has several rows for each probe. Each of these rows has the same PID, camera and video values, but different time, latitude and longitude values. The key for this table can be represented as a functional dependency. IJTLN tends to CY, where N stands for longitude. There is another dependency, P tends to CV. This relation is therefore not in BCNF. Indeed, it is not even in 3NF. We can decollapse probes to obtain a BCNF schema. Drawbacks of relational database management system. Representing videos as blobs learns that we have to write application code in an external language to manipulate a video object in the database. Each probe has an associated sequence of location readings is obscured, and the sequence information associated with the probe is dispersed and across several tupules. We are forced to separate that video information from the sequence information for a probe. These limitations are exposed by queries that require us to consider all the information associated with each probe. An object relational database management system database design. An object relational database management system supports a much better solution. First, we can store the video as an ADT object and write methods that capture any special manipulation we wish to perform. Second, because we are allowed to store structured types such as list, we can store location sequence for a probe in a single tuple along with the video information. This layout eliminates the need for joins in queries that involve both the sequence and video information. An object relational database management system designed for our example consists of a single relation called probes underscore all info. This definition involves two new types, location underscore sequence and mpeg underscore stream. The mpeg underscore stream type is defined as an ADT with a method display that takes a start time and an end time and displays the portion of the video recorded during that interval. This method can be implemented efficiently by looking at the total recording duration and the total length of the video and interpolating to extract the segment recorded during the interval specified in the query. Our first query in extended SQL using this display method follows. We now retrieve only the required segment of the video rather than the entire video. Now consider the location underscore sequence type. We could define it as a list type containing a list of row type objects. Consider the logseq field in a row for a given probe. This field contains a list of rows, each of which has 3 fields. If the object relational database management system implements collection types in their full generality, we should be able to extract the time column from this list to obtain a list of timestamp values and apply the MIN aggregate operator to this list to find the earliest time at which the given probe recorded. Such support for collection types would enable us to express our second query thus. Object identity. We now discuss some of the consequences of using reference type or aids. The use of aids is especially significant when the size of the object is large, either because it is a structured data type or because it is a big object such as an image. Although reference types and structured types seem similar, they are actually quite different. There are important differences in the way that database updates affect these two types. Deletion. Objects with references can be affected by the deletion of objects that they reference, while reference-free structured objects are not affected by deletion of other objects. For example, if the theaters table were dropped from the database, an object of type theater might change value to null because the theater underscore t object it refers to has been deleted, while a similar object of type my underscore theater would not change value. Update. Objects of reference types change value if the referenced object is updated. Objects of reference pre-structured types change value only if updated directly. Sharing versus copying. An identified object can be referenced by multiple reference types so that each update to the object is reflected in many places. To get a similar effect in reference, pre-type requires updating all copies of an object. There are also important storage distinctions between reference types and non-reference types which might affect performance. Storage overhead. Storing copies of a large value in a multiple structure type, objects may use much more space than storing the value once and referring to it elsewhere through reference type objects. This additional storage requirement can affect both disk usage and buffer. Clustering. The subparts of a structured object are typically stored together on disk. Objects with references may point to other objects that are far away on the disk, and the disk arm may require significant movement to assemble the object and its references together. Structured objects can thus be more efficient than reference types if they are typically accessed in their entirety. Many of these issues also arise in traditional programming languages such as C or Pascal, which distinguish between the notions of referring to objects by value and by reference. In database design, the choice between using a structured type or a reference type typically includes consideration of the storage cost, clustering issues, and the effect of updates. Object identity versus foreign keys. Using an OID to refer to an object is similar to using a foreign key to refer to a tuple in another relation, but not quite the same. An OID can point to an object of theta underscore t that is stored anywhere in the database, even in a field, whereas a foreign key reference is constrained to point to an object in a particular referenced relation. This restriction makes it possible for the DBMS to provide much greater support for referential integrity than for arbitrary aid pointers. In general, if an object is deleted while there are still OID pointers to it, at the best the DBMS can do is to recognize the situation by maintaining a reference count. Therefore, the responsibility for avoiding dangling references rests largely with the user if OIDs are used to refer to objects. Extending the ER model. We use an extended ER model that supports structured attributes, distinguishes whether entities have object IDs, and allows us to model entities whose attributes include methods. The definition of probes has two aspects. First, it has a structured type attribute list of row, time, lat, long. Each value assigned to this attribute in props entity is a list of tuples with 3 fields. Second, props has an attribute called video that is an abstract data type object, which is indicated by a dark oval for this attribute with a dark line connecting it to props. Further, this attribute has an attribute of its own, which is a method for the j given dt. Alternatively, we could model each video as an entity by using an entity set called videos. The association between props, entities, and videos entities could then be captured by defining a relationship set that links them. Since each video is collected by precisely one probe and every video is collected by same probe, this relationship can be maintained by simply storing a reference to a probe object with each video's entity. This technique is essentially the second translation approach from ER. If we also make videos a weak entity set in this alternative design, we can add a referential integrity constraint that causes a video's entity to be deleted when the corresponding probe's entity is deleted. More generally, this alternative design illustrates a strong similarity between storing references to objects and foreign keys. The foreign key mechanism achieves the same effect as storing weights but in a controlled channel. If weights are used, the user must ensure that there are no dangling references when an object is deleted with very little support from the DBMS. Finally, we note that a significant extension to the ER model is required to support the design of nested collections. Using nested collections. Nested collections offer great modeling power but also raise difficult design decisions. Consider the following way to model location sequences. This is a good choice if the important queries in the workload require us to look at the location sequence for a particular probe. As in the query, for each probe, print the earliest time at which it recorded and the camera type. On the other hand, consider a query that requires us to look at all location sequences. Find the earliest time at which a recording exists for laugh equal to 5, long equal to 90. This query can be answered more efficiently if the following schema is used. The The choice of schema must therefore be guided by the expected workload. As another example, consider the following schema. If tuples in this table are to be interpreted as course CID can be taught by any of the teachers in the teachers field at a post sal, then we have the option of using the following schema instead. Daplax. The Daplax database language, Smith et al. 1983, Daplax Users Manual 1984 provides database definition and data manipulation capabilities based on the functional data model. The database definitions define the logical types and structures of information in databases and the constraints that specify which values are legal. The database manipulation capabilities allow a user to create, delete, modify, and retrieve information in databases. Daplax database definitions and database constructs. Daplax database definitions are syntactically similar to programming language declarations. The basic data definition constructs of a Daplax database are entity types, functions, and generalization hierarchies. An entity corresponds to a real-world object or condition. Student, faculty, and course are examples of entity types that could be present in a university database. Employees, managers, specialists, or entity types present in a company database. The types of entities that will be used as examples in this section are shown in this graphical representation of Daplax databases. Boxes represent types of entities. The name of each entity type is mentioned above the relevant box. Functions can be applied to entities to return the attributes or properties of those entities. For example, the name function can be applied to a faculty entity to return the faculty member's name. Similarly, the grade point average GPA function can be applied to a student entity to return the student's grade point average. Functions can also return sets of values. For example, a phone function applied to a faculty entity could return the set of phone numbers at which a faculty member could be reached. The types of functions discussed so far have string or numeric values. In addition, functions can be entity valued to model relationships between entities. For example, the advisor function, when applied to a student entity, returns the faculty entity that corresponds to the advisor of the given student. The enrollments function is an example of a set-valued entity function. Shows the functions that will be used in the examples in this section. Single-valued string and numeric functions of an entity type are listed within the entity type box. Set-valued string and numeric functions are listed within the entity type box and are enclosed in braces. Entity valued functions are represented by labeled arrows between the boxes. Single-headed arrows represent single-valued functions and double-headed arrows represent set-valued functions. The key concept behind Daplax and the functional data model is that all properties or characteristics of an entity are represented by functions applied to that entity. Daplax thus provides one unifying construct for properties rather than separate constructs for single valued and set valued properties or separate constructs for string valued, scalar valued and entity valued properties. In Daplax, entities can be grouped into generalization hierarchies. These hierarchies are used when one type of entity is more general than other type of entity. For example, a person entity type could be defined as a generalization of the student and faculty entity types. Person is considered more general because every student or faculty entity is also a person. we say that person is a supertype that as subtypes student and faculty. We say that a student is ISA person and that a faculty member is an ISA person. In Daplex, the functions associated with the supertype entity can also be applied to a subtype entity. Thus, the name function that is associated with the entity type person is inherited by the student and faculty entities. Figure 2.13, A minus D pictorially represents the database that will be used in the examples in the next function. The double arrows labeled ISA are used to represent membership in a generalization hierarchy. This database is simplified subset of the database defined earlier. Daplex operations. Database manipulation. The Daplex data manipulation language allows users to retrieve and update entities and functions values in the database. In the preceding section, we presented an overview of how entities are accessed in the database, an overview of update operations that are supported by Daplex is given in a data section. Database intervals. This section describes Daplex looping and printing statements. The for each statement is the basis for Daplex data retrieval. It is used to specify the set of entities or values that are to be accessed and to be looped over. The print line statement is used to print the function values of those entities. Several example queries of increasing complexity are presented now. Number 1. For each student, print the student's name and GPA. Number 2. For each student, print the student's name, GPA and name of the student's advisor. Number 3. For each student who has a GPA greater than 3.0, print the student's name, GPA and the advisor's name. Number 4. For each student who has a GPA greater than 3.0, print the student's name, GPA, the advisor's name and the entities of 3 credit courses for which the student has enrolled. This example specifies that for each student in the database, the name and GPA should be printed. The set of all students in the database is specified by the constructor. Student. The iteration over the set is specified by the constructor. For each S in loop, end loop. The body of the loop, in this case, the print line statement is executed. Once for each student, we refer to S as the loop parameter. Functions can be applied to the loop parameter S by using a parenthetical functional notation as in the following: name S, GPA S. These are to be read as name of S and GPA of S respectively. The fact that name is defined for the supertype person and not for the subtype student makes no difference in how it is used. The inherited function name can be applied to a student entity in exactly the same way as the GPA function can be applied. Example 2. In this example, the name of each student's advisor in addition to the student's name and GPA is printed. The only addition is the expression name of advisor. The construct advisors applies the advisor function to the student S and returns the faculty entity that corresponds to the student's advisor. The name function is then applied to the faculty entity and the resulting string value is printed. The entire construct is read as name of advisor of S. This construct is an example of functional composition. A powerful Laplace functional composition permits the user to think of functions of related entities as additional properties of values associated with the original entity. Example 3. In this example, the student's name, the GPA values and the advisor's name are printed only for those students who have a GPA higher than 3.0. The expression defines a qualified set of students. For each student in this set, the name, GPA and advisor's name are printed. We say that the expression GPA of S greater than 3.0 qualifies the set of students. In general, the qualification can contain a complex Boolean expression involving conjunctions and conditions, disjunctions or conditions, and existential for some and universal for be given a re or for no qualification. Example 4. This example illustrates the use of nested iteration. After the name, the GPA and the advisor's name for a given student are printed. The 3 credit courses in which the student is enrolled are accessed and their titles printed. The expression enrollments of S defines the set of courses in which a student is enrolled. The enrollments function applied to a student S returns that set of courses. The reader may note that a different set of courses is returned for each student. The qualification where credit of C equal to 3 restricts each set of courses to include only 3 credit courses. We then print the titles of those courses. In general, the for loop can be nested to any level. These examples illustrate the basic Laplace construct for set expressions, qualifications, and iterations. The programming language term Laplace is a strongly typed expression language. A function applied to an entity is an expression that has a certain value. The value can be string, scalar, or entity. For example, the expression name of S as a value of type character string. The expression advisor of S as a value of type faculty entity. The value of an expression can also be a set. The expression enrollment of S as a set value, the members of which are course entities. Similarly, for a faculty entity P, the expression phones of P as a set value, the members of which are strings. The entity type names themselves are set expressions. The expression student as a set value, the members of which are all student entities. Similarly, faculty and course are set expressions. A set valued expression can be qualified to restrict the set of values. For example, the expression S in student where GPA of S greater than 3.0 restricts the set of student entities to those who have a GPA greater than 3.0. Similarly, the expression C in enrollments of S where credits of C equal to 3 restricts the set of students courses to 3 credit courses. Note that in both these cases, the result of a qualification is a subset of the original set. In the examples in this section, set expressions have been used to control the iteration of the for each loops. The body of a loop is executed once for each qualified element of the set. Database update. There are 2 types of values that can be updated in a Laplace database: the function values of existing entities and the sets of entity types themselves. For a given student, update the student's GPA. For a given student, add a course to the student's enrollments function. Create a new student entity. Change that student to an instructor entity. ER model. The entity relationship ER model. The ER model is capable of incorporating important semantic information about the real world and offered more data independence than the conventional hierarchical network and relational models. The model presents a framework from which the three conventional models could be derived. ER diagram was introduced as a tool for database design. The ER model constructs. The basic constructs of the ER model comprise entity and relationship, entity set, relationship set, rule, and value are also defined. These terms are defined as follows. An entity is a thing which can be distinctly identified, such as person, post, salary, task, etc. A relationship is an association of entities such as employer, employee, parent, child, etc. While an application environment may consist of a large number of entities and their interrelationships, only a specified few may actually enter the database definition. An entity set is defined as a set of entities which have a certain relationship. An entity belonging to an entity set has properties in common with other entities in the set. A relationship set R is a mathematical relation among n entities, each taken from an entity set E1, E2, E3, En, divided by E1 belongs to capital E1, comma E2 belongs to capital E2, comma En belongs to capital En, and each tuple of entities E1, E2, En is a relationship. The role of an entity in a relationship is the function that it performs in the relationship. For example, husband, brother, neighbor are roles of an entity. The value is the actual data value, occurrence of an entity. Blue, Kumar, 4, etc. are values. Value sets are classifications of values, that is, color, name, etc. An attribute is a function which maps from an entity set or relationship set into a value set or a Cartesian product of value sets. A schema of the real world is represented in the ER model by a graphic method which connects entity types, sets and relationships. Relationships can be one-to-one, many-to-one, one-to-many, and many-to-many. Data can be viewed from 4 levels. Information concerning entities and the relationships as conceived by a database designer. Information structure, organization of information in which entities and their interrelationships are represented by data. Access path independent data structure, access path dependent data structure involving search and indexing schemes. While the conventional network model attempts to achieve point 4, the relational model concerns itself with points 2 and 3. It must be noted that the ER model does not define entity type hierarchies as represented by the ISA relationships, such as generalization, aggregation, etc. ER model representation and employee details. As shown, ER model operations. Since the ER model was originally conceived by Chen more as a tool for systems analysis, design, and documentation, he did not propose any manipulate commands or operations on the basic constructs such as entity and relationship. The ER model framework was only used as a conceptual background to design a database, which itself would be finally represented in terms of the conventional network or relational models. The operations of the corresponding model so derived, that is, a network or relational model, were to be utilized for operations or manipulation of the data. Application of the ER model. The ER model presents itself as a tool for systems analysis and schema design. As most of the early models did, the schema design and its graphic representation through the ER model based schema are primarily designed for the purpose of articulating the overall data management functions, but the schema is not implemented. 10 identities, 4 steps in designing a database using the ER model. Identify entities and the sets and relationships and the sets. Identify the nature of the relationships, that is, whether 1 is to n or m is to n, etc. Define value sets and attributes. Organize data into entity relations, and also identify primary keys. By following these steps, it is possible to arrive at the ER diagram representing entities and the relationships, including the nature of the relationship 1 is to m, m is to 1, m is to n. The relational model can be derived from the ER model specification. To begin with, the functional dependencies can be easily identified from the ER model, which can, in turn, be utilized to define the normalized relations. It can also be shown that ER relations in this model are similar to the third normal form, NF relations, but with clearer semantics. Usually, the normalization process is resorted to in bottom-up refinement of unnormalized relations to first, second, and third normal forms respectively. In contrast, the ER model offers a top-down approach to normalization, definition of third normal form relations starting with the ER representation. The derivation of the network model from the ER model definition is also straightforward, with each entity represented by a rectangle being a record type and the arrow identifying the relationship 1 is to n or m is to n, defining the number of member records the owner may own, the arrow originating in the owner and terminating in the member. Conclusion: the ER model, being the predecessor of semantic models, though it was then not referred to as a semantic model, brings out the essential concept of an entity or later object and its relationship with other entities. It, however, does not bring out the structure of an entity in terms of type hierarchies such as aggregation, etc., which later became essential characteristics of a semantic model. The model's most important objective and applications was in terms of its ability to serve as an effective tool for systems analysis and database design, while the database itself could be implemented within the framework of any of the conventional models, namely network or relational data models, which could also be derived from ER schemas. The ER model has been a success as a conceptual tool used even today in conceptual modeling and object-oriented analysis and design. Some software engineering (CASE) tools have been developed incorporating the ER model for the system lifecycle phases of analysis and design only, while the system implementation phase may continue to be in the conventional or DBMS, Relational Database Management Systems, IFO. While the fundamental principles concerning semantic database models and systems are basically widely agreed upon, investigations of semantic database issues have given rise to the IFO model. So far, only the structural components of the IFO has been defined. The data manipulation and integrity specification components are yet to be defined. Therefore, only the IFO constructs are described in the following sections and not the operations. The IFO model Abhidibau and Hull 1987 attempts to mathematically define the 4 fundamental principles of semantic data modeling, widely accepted and reflected in the various models covered in earlier chapters. Number 1. Data about objects and their interrelationships should be modeled in a direct manner. Number 2. Object-based modeling as above permit the database designers and users to conceive the application environment in terms of objects of the real world without the indirection resulting from the symbolic identifiers necessitated by records and pointers which the conventional record-based models require. Number 3. Type, subtype or class hierarchies are provided for classes and subclasses of object. Example, employees is a subtype persons in a manner similar to type hierarchies. Number 4. Aggregation, Cartesian product and grouping are provided for groups of objects. For example, address is the aggregate of house number, street and city. IFO incorporates these 4 principles on a mathematical basis supported by a graph-based representational framework. It therefore permits representation and evaluation of various relevant models also. Thus, IFO can serve as an analyst tool not only for representing the semantics of the data but also for evaluating the features and facilities repeat of various semantic models. IFO informal description. IFO attempts to graphically represent the schema of semantics of the real-world application environment. An IFO schema is a directed graph with vertices and graphs. A family of IFO instances is associated with each schema. They correspond to structural versions of dataset that can be represented using the schema. IFO consists of types that model the structure of these objects arising in a given database application. Fragments are built from type and represent functional relationships in the model. The ISA relationship between various objects is also incorporated in a manner analogous to the ISA in Daplex. Objects in IFO. An IFO schema is made up of object types or classes of objects. There are 3 atomic types and 2 constructs are available for building more complex types. The printable objects are of predefined types and act as a basis for input-output. In an IFO schema, they are graphically represented by square nodes. The names of the type of printable objects can be string, integer, boolean or picture, which are accordingly mentioned in the representation. Names associated with the nodes are called tokens and can be specified in the formal model. The second object type, called abstract, corresponds to objects which do not have a structure behind them. Example, person, object has attributes but no structure. An object structure is represented by a diamond with its name. The elements of an abstract type are not printable, but database users will be able to refer to these directly as existing entities using a printable type for names of abstract objects. Example, person names. The third atomic type is a pre-type and corresponds to entities obtained via an ISA relationship and is represented by a code. Their underlying structure is inherited via an ISA relationship. The presence of ISA relationships may cause objects with the complex structures to be associated with free vertices of a schema. Non-atomic types can be constructed by grouping atomic concept occurrences on similar lines as the equivalent grouping and mechanisms available in other models, like the grouping classes in SDM. As shown later, a star vertex at is used to depict the type corresponding to set of students in a class denoted as O student. Each set of students is an object with a particular structure. Further, the Cartesian product operator is a mechanism for constructing new types from existing ones. This is equivalent to aggregation type hierarchy described elsewhere in this book. A cross vertex represents the aggregation. The arc connect to types which together aggregate and or coordinates of a class. Illustration of aggregation. Fragments. Functional relationships among object types can be represented as fragments. These are very similar to functions in functional models such as Laplace, the important difference being that a distinction is made between vertices serving as domain and those serving as range. This permits hierarchical construction of IFO fragments, and a modular view of the IFO schema is an example of a fragment to represent a set of students with the function mapping into their grades printable. Indicate two functions on course, namely enrollment and course names. Nested functions are also permitted. An example of a fragment. ISA relationships. An ISA relationship is the equivalent of subtype, supertype, hierarchy relationships in other semantic models. The functions defined in the supertype are automatically inherited by the subtype. An ISA relationship can be either one of specification, subdivision 1, or one of generalization. Examples of specialization and generalization abound intuitively. Specialization defines the roles for members of a given type. A person may be a student. Generalization tends to, on the other hand, defines a different situation where distinct pre-existing types are combined to form new types. Example, a car and boat may be combined to form an ambiguous vehicle. In a case of specialization, the functions of the supertype object are automatically inherited by the subtype object, whereas in generalization, the reverse holds true, that is, the functions of a member are acquired by the group or there is upward inheritance. The IFO schema. The building blocks of the schema have already been defined in earlier subsections. These building blocks can be combined to form IFO schemas in the schematic design of a real-life database. Schematic design is basically a top-down process through iteration may occur beginning with the specification of major object types found in a real-world application environment. An IFO schematic designer will have to specify subsidiary object types defined or constructed, sub or supertypes as natural to the application environment, and finally specify all the functions of all the object types of the schema. A modular approach to schematic design in IFO is permitted, as is evident in the steps identified above. For example, fragments provide a natural representation of types and their functions. The reader can easily construct the IFO schema for a particular application environment. The following example describes a schema where each employee and student, who are both specialization subtypes of parents, owns a boat and a car, respectively, both of which generalize into an aggregate called the ambiguous vehicle. Figure 2.18. Object-Oriented Database Management System, ODMG Data Model, and ODL. Object-Oriented Database Management System. In the introduction of this chapter, we defined an object-oriented database management system as a programming language with the support of persistent objects. While this definition reflects the origins of object-oriented database management systems accurately, and to a certain extent the implementation focus of object-oriented database management systems, the fact that object-oriented database management systems support collection types makes it possible to provide a query language or collections. Indeed, a standard has been developed by the Object Database Management Group and is called Object Query Language. OQL is similar to SQL with a select from, where, style syntax, even, group by, having, and order by are supported. many of the proposed SQL 1999 extensions. Notably, OQL supports the structured types including sets, bags, arrays, and a list. The OQL treatment of collections is more uniform than SQL 1999 in that it does not give special treatment to collections of rows. For example, OQL allows the aggregate operation count to be applied to a list to compute the length of the list. OQL also supports reference types, path expressions, ADTs, and inheritance, type extends, and SQL style nested queries. There is also a standard data definition language for object-oriented database management systems, object data language or ODL, that is similar to the DDL subset of SQL but supports the additional features found in object-oriented database management systems such as ADT definitions. The ODMG data model and ODL. The ODMG data model is the basis for an OODBMS, just like the relational data model is the basis for an ODBMS. A database contains a collection of objects which are similar to entities in the ER model. Every object has a unique OID and a database contains collections of objects with similar properties. Such a collection is called a class. The properties of a class are specified using ODL and are of three kinds: attributes, relationships, and method. Attributes have an atomic type or a structured type. ODL supports the set, bag, list, array, and structured type constructors. These are just set of, bag of, list of, array, and row in the terminology. Relationships have a type that is either a reference to an object or a collection of such references. A relationship captures how an object is related to one or more objects of the same class or of a different class. A relationship in the ODMG model is just a binary relationship in the sense of the ER model. A relationship has a corresponding inverse relationship. Intuitively, it is the relationship in the other direction. Methods are functions that can be applied to objects of the class. There is no analog to methods in the ER or relational models. The keywords interface is used to define a class. For each interface, we can declare an extend, which is the name for the current set of objects of the class. The extend is analogous to the instance of a relation and the interface is analogous to the schema. If the user does not anticipate the need to work with the set of objects of a given class, it is sufficient to manipulate individual objects. The extend declaration can be omitted. ODL also allows us to specify inheritance hierarchies. OQL. The ODMG query language, OQL was deliberately designed to have syntax similar to SQL to make it easy for users familiar with SQL to learn OQL. Let us design with a query that finds pairs of movies and theaters such that the movie is shown at the theater and the theater is showing more than one movie. The select class indicates how we can give values to fields in the result. The two result fields are called mname and tname. The part of this query that differs from SQL is the from class. The variable m is bound in turn to each movie in the extend movies. For a given movie m, we bind the variable t in turn to each theater in the collection m shown at. Thus, the use of the path expression m shown at allows us to easily express a nested query. The following query illustrates the grouping construct in OQL. For each ticket price, we create a group of theaters with the ticket price. This group of theaters is the partition for that ticket price referred to using the OQL keyword partition. In the select class, for each ticket price, we compute the average number of movies shown at theaters in the partition for that ticket price. OQL supports an interesting variation of the grouping operation that is missing in SQL. The group by class now creates just two partitions called low and high. Each theater object T is placed in one of these partitions based on its ticket price. In the select class, low and high are Boolean variables exactly one of which is true in any given output tuple, partition is instantiated to the corresponding partition of theta objects. In our example, we get two result tupules. One of them has low equal to true and average number equal to the average number of movies shown at theaters with a low ticket price. The second tuple has I equal to true and average number equal to the average number of movies shown at theaters with the high ticket price. The next query illustrates OQL support for queries that returns collections other than set and multi-set. The order by class makes the result a list of theater names ordered by ticket price. The elements of a list can be referred to by position, starting with position O. Therefore, the expression extracts a list containing the names of the 5 theaters with the highest ticket prices. OQL also supports distinct having, explicit nesting of subqueries, view definitions, and other SQL features. Object hierarchies. To organize and interrelate these identified constructs, object-oriented database models utilize certain abstraction primitives. Basically, abstraction is the ability to hide details and concentrate on the general and common properties of a set of objects. In database modeling, abstractions are used to obtain group or categories of objects which share a certain common set of properties. Abstraction can also be used to combine categories of objects in more generalized categories. The principal abstractions in object-oriented data modeling are generalization, specialization, aggregation, classification. Association also is sometimes identified as an abstraction. Generalization. Generalization is a familiar concept in mathematics. Generalized expressions such as the concept of the nth term in a series are very commonly used. Generalization is essentially a process of extracting from one or more given classes of entities or objects the description of a more general class that captures commonalities of the objects within a particular class by suppressing some of the detailed differences in the descriptions of the given classes. Employee is a generalization of various types of employees such as engineer, manager, accountant, clerk, typist, etc., all belonging to the same class in an organization. Generalization can also be described as a primitive or generic kind of abstraction that relates a type to a more generic one. Example, employee as a subtype manager. These relationships organize types in a hierarchic manner. Subtypes contain subsets of objects among their supertypes. They may inherit all the properties of their supertypes and in addition have properties not defined for their supertypes. Several kinds of generalization hierarchies or type hierarchies are used to define the database schema structure. Strict hierarchies, trees, and directed acyclic graphs are two examples of type hierarchies. In directed acyclic graphs, unlike strict hierarchies, an object subtype may have more than one parent supertype. See below figure. Krishna Kumar with the name, address and spouse is simultaneously a subtype of manager, which itself a subtype of an employee, and also a management student, a subtype of student, since Krishna Kumar is a manager who also goes to study in a management school. Generalization is a very common hierarchical structure. It is known in almost every walk of life and is used consciously or unconsciously by one and all. Specialization. The converse of generalization, that is, the process that has an effect opposite to that of generalization, is called specialization. It creates a new class by introducing additional details to the description of the existing one. Thus, both processes, generalization and specialization, are applicable to a given level of entity hierarchies, also known as type hierarchies. This leads to identification of a supertype or subtype depending on whether the level is higher or lower in the type hierarchy. Specialization abstractions characterize the relationships defined by generalization primitives more intensely. Specialization primitives relate a type to a more generic one. But unlike subtype, supertype relationships, whether the union of subtype members is always equal to the set of supertype members. Example, as in below figure, the supertype vehicle has three subtypes: air, surface and water vehicles, where the set of supertype members is not necessarily equal to the union of its subtype members. Generalization and specialization constitute what is generally referred to as an ISA hierarchy, which determines the relative level of any object in the hierarchy. Aggregation. Aggregation is a conceptual process where a collection of concepts is treated as a single concept. This again is a very common process in day-to-day life. New names are assigned to concepts that are basically groupings or collections of other concepts, which in turn may themselves be groups of more elementary concepts. Most of our commonplace conceptual structures are aggregations. Example, a country is an aggregation of states, which are aggregations of districts, which in turn are aggregations of taluks, which are again aggregations of villages. Aggregation abstractions relate objects to their components. Example, Krishna Kumar, an instance of object person, is characterized by name, address and spouse. Object address comprises house number, street, city and pin code. Aggregation can be applied recursively to retrieve the components of an object, such as part of a part of a part of a part in mechanical assembly of parts. See below figure. Decomposition is the opposite of aggregation. It decomposes a class into its parts. For example, a country into states and a state into districts and so on. Classification. Classification involves grouping entities that share common properties in a class over which uniform conditions are applicable. For example, the class person can be derived from the entities Krishna Kumar, Bada, etc. Through classification. Like the other processes, it is again a commonplace conceptual process in real life. Classes or types of human beings, students, ships, aircraft, etc. are common. Classification of abstractions relates objects to their generic types. Example, Krishna Kumar is a member of the type person. For a specific object in a database, an organization that represents both generalization and classification relationships represents all its generic types. Thus, we see that the universally familiar notions in real life pertaining to grouping relationships among objects are represented in the literature of semantic database modeling as abstraction primitives or type hierarchies of generalization, specialization, aggregation, etc. Overview of Object Database Systems (OODBMS) Implementation and Challenges. OODBMS Implementation Challenges. The enhanced functionality of OODBMS raises several implementation challenges. Some of these are well understood and solutions have been implemented in products. Others are subjects of current research. In this section, we examine a few of the key challenges that arise in implementing an efficient, fully functional OODBMS. Storage and access methods. Since object relational databases store new types of data, OODBMS implementers need to revisit some of the storage and indexing issues. In particular, the system efficiently stores ADT objects and structured objects and provide efficient indexed access to both. Storing large ADT and structured type objects. Large ADT objects and structured objects complicate the layout of data on disk. This problem is well understood and has been solved in essentially all object relational database management systems and object-oriented database management systems. User-defined ADTs can be quite large. They can be bigger than a single disk page. Large ADTs like BLOBs require special storage, typically in a different location on disk from the tuples that contain them. Disk-based pointers are maintained from the tuples to the objects they contain. Structured objects can also be large, but unlike ADT objects, they often vary in size during the lifetime of a database. Indexing new types. One important reason for users to place the data in a database is to allow for efficient access via indexes. Unfortunately, the standard RDBMS, Relational Database Management System, index structures support only equality conditions, B plus trees, and hash indexes, and range conditions, B plus trees. An important issue for Object Relational Database Management System is to provide efficient indexes for ADT methods and operators on structured objects. Many specialized index structures have been proposed by researchers for particular applications such as cartography, genome research, 11 multimedia, repositories, web search, and so on. An object relational database management system company cannot possibly implement every index that has been invented. Instead, the set of index structures in an object relational database management system should be user extensible. Extensibility would allow an expert in cartography, for example, to not only register on AD1 for points on a map, that is latitude longitude pairs, but also implement an index structure that supports natural map queries. One way to make the set of index structures extensible is to publish an access method interface that lets users implement an index structure outside the database management system. The index and data can be stored in a file system, and the database management system simply issues the open, next, and close iterator requests to the user's external index code. Such functionality makes it possible for a user to connect a database management system to a web search engine, for example. A main drawback of this approach is that data in an external index is not protected by database management system support for concurrency and recovery. An alternative is for the object relational database management system to provide a generic template index structure that is sufficiently general to encompass most index structures that users might invent. Because a structure is implemented within the database management system, it can support high concurrency and recovery. The generalized structure tree GST is such a structure. It is a template index structure based on B plus trees, which allows most of the tree index structures invented so far to be implemented with only a few lines of user-defined ADT code. Query processing. ADTs and structured types call for functionally in processing queries in object relational database management systems. They also change a number of assumptions that affect efficiency of queries. User-defined aggregation functions. Since users are allowed to define new methods for ADTs, it is not unreasonable to expect them to want to define new aggregation functions for their ADTs as well. Most object relational database management systems allow users to register new aggregation functions with the system. To register an aggregation function, a user must implement three methods, which we call initiate, iterate, and terminate. The initiate method initializes the internal state for the aggregation. The iterate method updates that state for every tuple seen, while the terminate method computes the aggregation result based on the final state and then cleans up. As an example, consider an aggregation function to compute the second highest value field. The initialize call would allocate storage for the top two values. The iterate call would compare the current tuple's value with the top two and update the top two as necessary. And the terminate call would delete the storage for the top two values, returning a copy of the second highest value. Method security. ADTs give users the power to add code to the database management system. This power can be abused. A buggy or malicious ADT method can bring down the database server or even corrupt the database. The database management system must have mechanisms to prevent buggy or malicious user code from causing problems. One mechanism to prevent problems is to have the user methods be interpreted rather than compiled. The database management system can check that the method is well behaved either by restricting the power of the interpreted language or by ensuring that each step taken by a method is safe before executing it. Typical interpreted languages for this purpose include Java and the procedural portions of SQL 1999. An alternative mechanism is to allow users method to be compiled from a general purpose programming language such as C++ but to run those methods in a different address space than the database management system. In this case, the database management system sends explicit inter-process communications IPCs to the user method which sends IPCs back in return. This approach prevents bugs in the user methods. Example, stray pointers from corrupting the state of the DBMS or database and prevents malicious methods from reading or modifying the database management system state or database as well. Note that the user writing the method need not know that the database management system is running the method in a separate process. The user code can be linked with a wrapper that turns method invocations and return values into IPCs. Method caching. User-defined ADT methods can be very expensive to execute and can account for the bulk of the time spent in processing a query. During query processing, it may make sense to cache the results of methods in case they are invoked multiple times with the same argument. Within the scope of a single query, one can avoid calling a method twice on duplicate values in a column by either sorting the table on that column or using a hash-bashed scheme. An alternative is to maintain a cache of method inputs and matching outputs as a table in the database. Then, to find the value of a method on particular inputs, we essentially join the input tuples with the cache table. These two approaches can also be combined. Query languages for object-oriented databases, O2. O2, a product of the O2 technology operation, Versailles, France, is claimed to be a full-fledged object-oriented database management system, which includes application development environment and a set of GUI, graphic user interface, development tools. The product is sold as a set of modules as follows. The O2 engine is the heart of the system. The O2 runs in client, server, and LAN environments. It can be programmed in C, C++, or in O2, C, a database query language which includes an optimizer and uses an SQL type system, extended with the ability to handle structured and multimedia objects while still ensuring SQL compatibility. The O2 data model and language support. In the O2, a system consists of a set, a schema, and a database. A schema defines data types, while the database contains data itself. The O2 data model is the basis for O2, C language, a fourth generation language by the virtue of its ability to support programming, database manipulation, and user interface generation all in one. O2 handles values and objects which are to be distinguished. A value as a type which is recursively definable from atomic types and types constructors. An object, on the other hand, as an identity, a value, and a behavior defined by its method, and it belongs to a class. An object or value may refer to other objects through their identities. An object or value may be composed of subvalues. In the case of a value, a subvalue is a part of its container and cannot be shared by other objects. Automatic types are Boolean, character, integer, real, string, and bit. Complex types may be defined recursively using tuple, list, and set constructors. A list is an ordered collection whose elements are accessible by a subscript, behaves as a flexible and insertable array. A string behaves as a list of characters in which a bit value acts as a list of bytes. To become persistent, an object or value must be attached directly and tentatively to a persistent root, which is declared in a schema by giving a name to it. For data manipulation, persistence is transparent. O2 provides encapsulation at 3 levels: class, schema, and database. Class encapsulation. Common in object-oriented models, an attribute is private to a class by default but may be made accessible outside as a read-only or public attribute. A method may be private or public. Schema encapsulation. A schema is a set of class definitions. A schema may export some classes and thereby allow other schemata to reuse, import them. It permits the object-oriented programming at large. Database encapsulation. The database itself, that is, actual data, can be encapsulated. An application running on a particular database may access another database involving a method which will run against the remute database. This allows reutilization of data and permits communications with other possible and heterogeneous databases. Query language. O2 SQL is an SQL-like query language extended to deal with complex values and objects. O2 SQL is a subset of O2 C but can be used independently as an ad hoc interactive query language or as a function callable from C or C++. All O2 data types, operations, and methods are allowed inside a query. The select part of a query defines the structure of the result. The from part introduces the names of persistent sets and the list against which the query will run, and finally the where class introduces the predicate that filters the results. For example, retrieves the restaurants in Bombay which change less than ₹100 and the menu choices available. The O2 engine. The O2 engine is the main kernel of O2 database management system, providing support for accessing and updating large shared data which is persistent, reliable, and secure. The O2 engine should therefore support subdivision A, persistence, both orthogonal and transparent; subdivision B, transaction management; and subdivision C, a schema evaluation mechanism. At the modeling level, the O2 engine will support all the features of an O2 data model: complex and identifiable objects, classes, types, encapsulation, methods, multiple inheritance, overriding, and late binding of methods. The architecture of the O2 engine comprises 3 main layers: the upper schema manager, the middle object manager, and the innermost disk store manager. The schema manager handles all database schema related aspects as creation, retrieval, update, and deletion of classes, methods, and global names. The import mechanism between schemas is also handled by it. It also enforces the semantics of inheritance and performance consistency checks on a schema. The object manager handles object with identity, passes messages and also manages structured values and their structural operations. It implements persistence, performs garbage collection of unreferred objects, implements influxes and clustering strategies based on complex objects and inheritance. The disk manager provides the conventional persistent storage and structures as record structured sequential files, B trees and hashcode indexes and long data items. These structures are finally mapped into data storage pages on a disk. The pages form the basic units of persistent data storage. Locking is provided for concurrency control and a write ahead lock technique is used for rollback and recovery. The disk manager of O2 is an extension of WISS Wincosin storage system in terms of rollback and recovery functions and client server architecture. The client server architecture of the O2 engine is a page server since it deals only with pages and does not understand the semantic of the object. The page server architecture provides the advantage of planning most of the complexity of the system within the workstation, leaving the server to perform tasks it alone can perform. Since the concept of object is not understood by the server, no queries or methods can be issued on the server for execution. However, large arrays of data can be accessed through indexes. Calls are made to the input-output level of the storage system for execution. The schema manager performs the housekeeping of schema definition, whether complete or temporarily partial. It performs consistency checks, especially for incomplete schema definitions which are permitted. Consistency management for activities such as class deletions, complete or partial, etc. are taken care of by the schema manager. However, deletion of a class which is not a leaf in the hierarchy is not permitted. If the deleted class appears in the signature of a method of another class, the method body is invalidated. The schema manager maintains the linkages between databases and schemas. For example, several databases may be attached to the same schema, or a database may be physically stored on different disk volumes. A program may invoke methods of an imported class in a database attached to the schema from which the class was imported. In such cases, the method may return objects belonging to the remote database which is referenced by objects of a local database. Persistence or persistent storage is implemented in the O2 by identifying a reference count with each object. When a given object is made persistent, all its components also automatically become persistent. Persistence is the capability to store the object beyond the runtime session of the procedure in C++, which should often else be transient. Objects and values are always created initially as transient, not persistent. When an object becomes persistent for the first time, it has to be placed in a persistent space, that is, a disk page. Cluster trees are physical information and are attached to a specific database of a given logical schema. A cluster tree expresses the way in which a complex object and its components will be physically stored or clustered together. Cluster trees are also definable for collections of named objects or values as sets, bags, or lists. Conflicts may arise in clustering due to sharing. DBA can control the placement of an object and values for preventing and resolving such conflicts, and that may be activated by priority ordering of cluster trees. If no cluster tree is defined for any objects or values, they are promoted to persistent space immediately. However, in cases where clustering information is specified, promotion to persistent space is delayed until transaction commit time, because at update time the system has only an incomplete view of the graph of objects. Space for an object in memory and disk is garbage collected from the environment. Space will be recovered while exiting from a block in a method and also when no reference is made by any other persistent object or value. Objects and values are represented in terms of records. The format of objects is identical in memory and on disk. Persistent records are manipulated directly on the page where they reside. Non-atomic values are decomposed into records on type constructor boundaries. Atomic values are embedded in their parent record except for large strings which overflow over several records. An object and the root of its value are stored in one record. Record identifiers are used as persistent identifiers for objects and also as pointers for constructed values. Objects and values have an identical memory representation. Values are handled differently. The addressing schema in the O2 engine comprises storing objects or values in records addressed by their physical record identifiers, reflecting the location on the disk. The structure of physical addresses: volume identifiers 2 bytes, page identifiers in a volume 4 bytes, slot number 2 bytes, which addresses a record within a page. The O2 engine uses a two-level addressing mechanism with A, record identifiers on disk, and B, handles for records in memory. Each handle denotes a distinct record containing a value or an object. Handles serve as a uniform means to reference objects and values, persistent or temporary. This uniformity permits a temporary record storing an object or value to be promoted to persistent space at commit time. If early promotion occurs, a persistent identifier is generated and stored within the parent record. Otherwise, the handle is stored within the parent record and replaced with a persistent identifier later. The transaction management in the O2 engine comprises basically concurrency control and recovery mechanisms. Concurrency control is handled with a hierarchical two-phase locking protocol on files and pages. The lock is handled by the server and basically a redo log. The global lock manager runs on the server and the local lock manager catching the set of granted locks runs on the workstation. When a transaction updates or modifies the contents of a record within a given page, it asks for a lock from the local lock manager, which in turn either has a lock or asks for it from the global lock manager. If the lock is granted, then the update transaction is performed by it and the system generates a redo lock entry for the modified record in the workstation. These log records are written to a cache of log pages which is sent asynchronously to the server. If a modified page is to be sent to the server, the log cache is sent first. Indexing is essential for optimizing retrieval time and the indexes will be used by the O2 SQL optimizer. Indexes may be defined or named object or value collections. Inheritance will naturally be taken care of while an index is used. Indexes may be defined not only immediate attributes of an object but also on attributes of attribute, that is a composition path. O2 look, the user interface facility. O2 is a graphic user interface GUI, support facility and support display and manipulation of large complex multimedia objects on the screen. It allows the programmer to create simple but high quality graphic user interfaces quickly using ready-made object presentation on the screen, thus improving the productivity and speed efficiency. Rapid prototyping is facilitated by ready-made presentations customized to specific requirements. Colors, fonts and layouts can be redefined. The O2 look can build a ready-made multimedia presentation of an object. A pop-up menu allows the user to activate any of the object's methods. It permits editing of presentations, and after completing editing, the object can be written back to the database. Masks and other resources can be effectively utilized for custom building of an application for ready-made presentation. Mask is a structure used to express parts of an object which should be visible and editable. It also helps in naming the graphic components. A resource can be any graphic parameter such as background color, title, font, layout, menu, items, etc. Since resource files are interpreted only at runtime, O2 log allows customization of the user interface of an application without recompilation. O2look supports both English and French resource files and permits instantaneous switching between the two. Query languages for object-oriented databases. Gemstone. Gemstone, historically the first attempt to extend the features of object-oriented programming into a database environment, was very close to Smalltalk in many aspects. Gemstone object data model and language support. The Gemstone object data model is similar to that of Smalltalk. Goldberg, Robson, 1983, although Gemstone itself was written in C. Objects in Gemstone comprise collections of instance, variables, and methods. Each object has a stored object identifier called an OOP for object-oriented pointer, which is 32-bit signed integer value. Methods procedures in Gemstone are written in the OPAL programming language. OPAL provides facilities for persistent objects, concurrent access, transactions, and indexing, but lacks facilities for creating and manipulating user interfaces. Since it is expected these will be handled by application programs written in other programming languages. An example of object class definition in Gemstone is the instance variable names. Part of the declaration specifies the literal names of the instance variables of the object. In this case, there are 5. Part ID containing the OOP of an integer object. Part name containing the OOP of a character string. Subparts containing the OOP of a set object containing the subparts of the part. Is part of containing the OOP of a set containing the parts. Graphic containing the OOP of an object of type. Graphical object, which is the iconic representation of the part. It would also be necessary to define the object class of object containing set of parts. These objects would serve as values of the subpart and is part of instance variables. In OPAL, as in Smalltalk, instance variables are not necessarily constrained to contain only objects of specific types. The constraints part of the declaration can be used to specify such constraints. In class part, only 2 instance variables are constrained. Part ID is constrained to contain only integer objects, and part name is constrained to contain only string objects. In class part set, the set is constrained to contain only part objects. The constraint mechanism in OPAL is not intended to be a general purpose type checking facility, but is intended to constrain instance variables over which indexes will be constructed to enable fast retrieval. The remaining parts of the declarations, such as class variables, etc., are irrelevant to this discussion but were included for completeness. After the classes have been created, method declarations are used to specify the externally accessible behavior of the object. In case of part, a pair of methods is defined for object instance variable, one to access it and one to assign a value to it. For example, the accessing and assignment methods for the part name and subparts instance variables are in this method, A denotes return the value of equal to denotes ordinary assignment and percentage is a terminator. Methods are inherited by classes from the superclasses. In this example, both classes inherit the new method for creating new instances. Part set inherits method for adding and removing part objects from its superclass set. Once the classes and methods are defined, objects can be created and manipulated using the method. For example, if an object myPart exists in the database, the message myPart name asks myPart to return its part name. MyPart is referred to as the message's receiver, the object to which the message is addressed, while part name is the message's selector, specifying the method to be executed in response to the message. Class partset inherits methods from its superclasses, specifically class collection, a superclass of set allowing it to be searched for objects with instance variables satisfying certain conditions. For example, the following expression would return all of the part objects that are AND gates from a part set object myParts. Tuning the performance of object access is also possible. For example, class object defines the basic clustering message cluster which is inherited by all objects. The simplest clustering method simply assigns the receiving object to a disk page. It does not attempt to cluster related objects pointed to by the receiving object's instance variables. Special clustering methods can be defined for individual object classes. For example, the following defines a method cluster part for objects of class part. The message myPart cluster part would then cause the part object myPart to cluster itself. In this case, the method first asks myPart to assign itself to a disk page. Self-cluster does this and then asks other objects pointed to by specified instance variables to cluster themselves on the same page or a nearby page as myPart. For example, part name cluster asks the string object pointed by myPart's part name instance variable to cluster itself near myPart. Architectural features of gemstone. Figure 2 illustrates a single host gemstone architecture wherein a host computer, a Sun, 3 or 4 or VAX VMS runs a single database monitor process or Stone. Stone manages user login, logout operations, coordinates concurrent access by multiple users, and handles recovery. Each client process is associated with the gemstone session process or gem. Each gem process incorporates a data management kernel and an interpreter for OPAL. The gem processes communicate with the database monitor through inter-process communication mechanisms. A gemstone configuration may include multiple hosts in the network, and a client can simultaneously access databases on multiple hosts. However, a given database cannot be spread over multiple hosts. The user interface to each gem process is provided by a program running as a separate process on the host machine itself or on a workstation connected to the host. These gemstone interface programs call on libraries of C functions or Smalltalk object classes known respectively as the gemstone C or Smalltalk interface. A special purpose gemstone interface, the OPAL programming environment, is provided for application development, and it contains various editors and tools for use in program development. Workstations supported include the Sun 3 or 4 using Parkplace Smalltalk or C, the Macintosh 2 using Parkplace Smalltalk, and the IBM PC using Smalltalk V286 or Microsoft C. The gemstone architecture is a client-server architecture, though it differs in some aspects from the standard client-server architecture. Firstly, though it appears from figure taken from gemstone product documentation that the gemstone sessions must go through the database monitor in order to access the database. This may not always be true. The database monitor allocates object identifiers and performs transaction management functions. However, for ordinary database input-output operations, the gemstone sessions access the database directly, thus eliminating a potential performance bottleneck. Further, as OPAL is also capable of handling applications development, the programmer has a choice between C or Smalltalk in an application workstation, and OPAL is the host. The gemstone C and Smalltalk interface provides facilities necessary to allow external application programs and written in C or Smalltalk to access gemstone and its contained objects while maintaining internal object consistency within gemstone. Smalltalk interface provides a set of Smalltalk classes that allow a Smalltalk application to communicate with the gemstone database. Class gemstone represents the gemstone database itself. An application initiates a gemstone session by sending a log in message to the gemstone object. Instances of class gemstone object serve as proxies or representatives in the Smalltalk object space for corresponding objects in the gemstone database. Messages sent to these proxies by Smalltalk objects are forwarded to the corresponding gemstone object for execution. Class gemstone object also provides methods for replicating Smalltalk objects in the gemstone database and returning a gemstone object instance representing the new database object. Before an application can perform any useful work with the gemstone, it needs to know about certain gemstone objects. For example, in order to create and execute the OPAL text describing an operation on the gemstone database, the program needs a reference to a gemstone string class object so that it can first create a gemstone string object to contain the text. In Smalltalk, the dictionary special gemstone object contains a predefined set of instances of class gemstone object representing all kernel class objects in the gemstone database. This may be used by Smalltalk classes to provide a basic set of known gemstone objects. The gemstone database also maintains a directory of named objects for each user. Smalltalk objects can gain access to these named objects by sending a message to class gemstone, which returns an instance of class gemstone object in the Smalltalk object space corresponding to the gemstone object. This provides a mechanism for applications to gain access to an object stored in the gemstone database using an application defined name. Subsequent access to the object during the session can then take place via messages sent to the proxy of class gemstone object created in response to this message. For example, if an application had previously created a gemstone object of class part and named this object bold, A proxy to this object named local bolt could be created in the Smalltalk object space by sending the message. Similarly, the message a Smalltalk object as gemstone object could be used to replicate a Smalltalk object in the gemstone database. The Smalltalk interface provides two ways to send messages to gemstone database objects via their proxies, illustrated as follows. The first message as selector remote perform with the literal part name as a parameter designating the operation to be performed on gemstone. The second message as selector gs part name, which is the operation to be performed on gemstone, prefixed by gs to indicate that it is not to be performed locally by local bolt. Both these messages mean the same thing. Forward a message consisting of the selector part name to the gemstone object represented locally by the proxy local bolt. Arguments referenced in these messages may be either Smalltalk proxies of gemstone objects or local Smalltalk objects. If arguments are Smalltalk objects, they are replicated in the databases if possible before the message is sent, so that the message can be completely processed using objects local to gemstone. In either case, the result of the message will be returned to the Smalltalk program as a proxy of class gemstone object. The message passing mechanism makes use of objects replication messages understood by class gemstone object and its instances. These messages may be sent by any Smalltalk object to create replicas of Smalltalk objects in the gemstone database or to create Smalltalk versions of gemstone database objects. When a replica is created, everything referenced by the object being replicated is also replicated. Dictionaries are used to break cycles, such as when an object A being replicated references an object B and object B contains a reference to A and achieve closure. Even though gemstone C interface should have provided similar facilities, it may not do so because C is not object oriented and does not resemble gemstone to the same extent as Smalltalk does. For example, as in Smalltalk, both an object's OOP and a representation of the object's state may be imported into a C application's address space. However, access to objects directly in C circumvents object encapsulation and must be done with caution. In the C program alters the structure of an object, the object may no longer behave as expected. A C program can use only predefined OOPs or OOPs it has received from gemstone. The program cannot create new OOPs directly since these might be in conflict with OOPs already existing in gemstone. Functions are available to import and export individual objects of the various classes. As with Smalltalk applications before, a C application can perform any useful work, it needs to know the identities of certain gemstone objects such as basic class objects. In Smalltalk, this was done by providing a predefined set of Smalltalk proxy objects. However, in C, this is done differently. The object identifiers of a set of useful objects are made available as part of an include file, which can be used by the C compiler in generating code for programs calling gemstone. This file contains a set of predefined OOPs together with symbols for each one. These include the values nil, true, false, and each of the OPAL kernel classes. Since OPAL is used to define methods for a shared database, OPAL differs from most programming languages in permitting concurrent access by many users to the same data objects. The application program must take care in synchronizing the state of its Smalltalk objects or C structures and the state of the database. An application commits a transaction by sending at the OPAL level the message system commit transaction. Prior to this, an application must have exported to Gemstone from its address space any newly created or modified objects. In case the commit fails due to conflicts, the command system about transaction should be sent by the application. The concurrency control mechanism used is optimistic. Initially, an OPAL transaction operates as a private copy of Gemstone object in an area named workspace. Any modified objects in the workspace will be merged with the main shared object store only when the commit is performed by the transaction. At that specific point of time, it is checked whether any other transactions have been committed after the previous commit, which may have affected a change on the objects being read or modified by the first transaction. If yes, the commit is now refused. When such refusal takes place, the workspace is left intact, thus permitting the application to perform any cleanup or saving results generated during transaction and then abort the transaction. This begins a new transaction and creates a new workspace containing up-to-date copies of the shared and committed objects. A read-only transaction can always commit since no workspace modifications can be created by it. Such optimistic strategy evidently provides good concurrency when the number of conflicts is expected to be low. Gemstone also supports the conventional pessimistic concurrency control mechanism based on looking, which reduces concurrency. Thus, a choice between the two mechanisms can be made depending on the case. Objects that are unlikely to produce a conflict can be accessed optimistically, thereby providing greater concurrency, and transactions that are likely to engage in conflict can use the pessimistic conventional mechanism. Gemstone also supports a cooperative mechanism in which multiple applications cooperate in performing session management functions. Once a registered application initiates a transaction, all other registered applications are asked to approve the operation before it takes place. SQL Gemstone interface was also developed, and it permits Gemstone applications and OPAL methods to respond to SQL queries to an external relational database management system, and the query results are imported back as Gemstone objects for further processing. A C++ interface is also available. This interface comprises two components: a Gemstone C++ class library, which can be used in C++ directly to create persistent objects or to derive additional persistent classes, and a registrar utility that creates a runtime interface between a C++ program and a Gemstone database. A link between a Gemstone database and an NExpert object expert system shell is also developed by the Servologic Corporation. It supports a set of predicate functions which can be used within NExpert to retrieve objects from Gemstone and store them in NExpert, and a database link for performing the usual database operations. It is estimated that about 100 application sites were operational with Gemstone in the early 1990s. Performance of Gemstone is, however, average in terms of speed due to large overheads involved in processing and internal mapping. Query languages for object-oriented databases: Object Store. Object Store, object design in C, 1989, is an object-oriented database management system, product of object design in C, Burlington, Massachusetts, USA. The Object Store data model is based on C++. It supports extended data management capabilities as long and nested transactions. Version and configuration management, views, rules and linking facilities, source level debugging tools, a graphical interactive database browsing and querying capabilities are also provided along with the SQL interface. Object Store runs in Unix, OS2 and X Windows. Object Store object data model and language. Object Store based on the object model of C++, supporting features such as class hierarchies, object attributes, direct inter-object relationships, and user-defined encapsulated data representations. See ONTOS for examples. Object Store aims to minimize the difficulty of modifying native C and C++ application software to run over Object Store, and a number of facilities in Object Store support this. In Object Store, persistence is specified at the level of the individual object or variable rather than at the type level, so that functions return to operate or non-persistent data can also operate on persistent data. This also enables C++ programs to be converted to run on Object Store without changing existing type declarations or writing new ones, thus providing maximum compatibility with the C++. Architectural features of Object Store. Object Store functions in a distributed client-server architecture. It attempts to preserve to the greatest extent possible the one object space view of a conventional application program, rather than the programmer having to deal with his own application object space and a separate database object space and explicit movement of objects between them. As in many database application programs, this all activities as dereferencing pointers to persistent objects, cache recovery, etc. are handled entirely by the system, transparent to the programmer. Object Store permits object clustering explicitly. Thus, the chance of retrieving an object from the main memory is increased. For example, if all the components of a part's assembly are clustered together, then the first reference to one of the components causes the entire assembly to be cached in the client memory. Subsequent references to components are processed at main memory speed instead of at the slow disk speed of retrieving an object. The programmer can specify that objects are to be allocated to a given database, to a specified segment of a database, or as close as possible to a specified object. Object Store offers facilities to minimize the overhead of moving data from disk to virtual memory by maintaining consistency between on-disk and in-memory object formats. Object Store supports conventional database transactions employing two-phase locking. Additional forms of transactions such as long or nested, as required in complex applications, are also provided. Versioning is also supported. Object Store supports the navigational access using direct object references typically required by design applications. Associate query access to collections of objects is also supported. Associative access is implemented using the for each loop and query expressions. For example, if a part class has been defined with an attribute part number and parts is a collection of part objects, the following query finds the part numbered 99,999. Both persistent and non-persistent data are handled equivalently. Indexes can be defined over collections of objects for improving the efficiency of every query processing as in a relational database management system. Object Store also provides an interactive graphical tool, Schema Designer, for defining object classes. The tool automatically generates the corresponding C++ class definition header files. Released in 1997, Object Store version 5.0 is a high-performance, object-oriented database management system tuned and tailored for the web, that is World Wide Web or WWW. Object Store 5.0 supports ODMG standard binding for Java objects. Object Design in C also produced freeware ODI PSC and low-priced ODI PSC Pro for Java persistence. ODI PSC is included in many products as Asymmetrix Supercode Java compiler and is licensed by Microsoft and Netscape. There is also available an app wizard for creating Object Store MFC applications easily under Microsoft Visual C++. Unix platforms are also supported. Object Store is available in standalone or client and or server environment. An interesting practical application in 1997 of Object Store to aviation industry resulted in ticketless travel for passengers of Southwest Airlines USA. The customers can make interactive online booking and reservation at home through the internet www World Wide Web as a HTML application. The transaction is served by Object Store Web Server. Relational model, Tasmania, RM given T. RM given T, the forerunner of semantic models, aims at providing the conventional relational database designer with a semantic view. Modeling features and constructs available in RM given T are relevant to the database designer only to the extent it enables him to model the database more closely to the real world in terms of entities and relationships, while the end user may still persist with the conventional relational model. RM given T was reportedly not aimed at immediate implementation, and also no direct implementations were subsequently reported, though it served as the basis for many a later semantic model. While logically using the ER model's original definitions of entity and relationship, the RM given T proceeds further to formalize a structured representation of entities and relationships, all of them being structures superimposed on the basic relational model. Therefore, RM given T may be identified as the forerunner of the category of semantic models, usually referred to as relational model extensions. The basic assumption underlying RM given T is that the real world can be modeled in terms of entities which are represented in terms of E-relations and P-relations, both of which are specialized forms of the general n-ary relation. E-relations are used to declare that the referred entities exist, while P-relations express the properties of the entities. These relationships may be in terms of hierarchies or associations between entities. A formal catalog structure is used to represent the relationships. The system therefore can enforce integrity constraints that are implied in the relationships expressed in the catalog. RM given T constructs entities, the types, supertypes, and type hierarchies. Entities can be defined with the basic relational model as the foundation. Informally, an entity is any distinguishable object, concrete or abstract. Since the database aims to model the real world made up of entities, it will be a model or representation of that perception. Entities can be conceived as forming types, subtypes, and supertypes. While entities forming a type share a common property, subtypes derive those properties from the supertypes. A given entity type and its immediate subtypes and supertypes constitute a type hierarchy, that is, the generalization hierarchy, as shown in. The properties of a given supertype will be automatically inherited by its immediate subtype and so on, down to the lowest level in the type hierarchy. Thus, the P relation of a supertype E relation will be applicable to lower level subtypes as well. Subtypes are not necessarily unique, that is, type hierarchies are not necessarily disjoint. A single entity may simultaneously be the subtype of several supertypes. Surrogates or system generated entity identifiers as distinguished from user defined entity identifiers such as primary keys. By definition, an operation defined by a create entity command will result in the system generating a new surrogate value for the entity, which will be permanently associated with it. By command destroy entity, the surrogate will be deleted. The user can therefore be responsible for creating an entity surrogate, though he may not know its actual value. While within the database, all entity identification analogous to a database record ID in a database management system network environment will be in terms of surrogates. Outside the database environment, user-defined primary keys may still continue to be used. E-domain, E-attributes, and E-relations. E-domain is the domain of all possible surrogate values for the entity. Attributes defined in this domain are referred to as E-attributes. The symbol C is to be used as the terminal character of each E-domain name. Example, SC is the name of the E-attribute containing surrogates for suppliers S. E-relation is a unitary relation that lists the surrogates of all entities of the type currently existing in the database. Hence, it serves as a primary reference point for an entity in the database. Entity integrity rules. E-relations can accept insertions and deletions but not updates. E-relation also does not accept null values. Properties and P-relations. Property is an immediate single-valued piece of information that describes the entity in some manner. S-name, city, status, etc. are properties of supplier entity. Thus, for the entity supplier, as shown, or P-relations, the database designer can at his discretion frame the P-relations. However, the set of P-relations has to satisfy the following conditions. The primary key of every P-relation is an E-attribute with the same name as a single attribute of the corresponding E-relation. No two P-relations of the set have attribute names in common except as in subdivision A. Creation of properties for surrogates and the insertion of corresponding types can be done using the typical relational database management system commands such as create, insert, etc. The user need not necessarily be aware of the existence of surrogates and properties in the database definition. Thus, RM given T is primarily meant for a database designer to whom alone its structures are visible, while the end user is aware of only the conventional relational model of the database. Property integrity rule. If a tuple appears in a P relation P, then its primary key value has to appear in the corresponding E relation. This rule ensures that operations such as insertion and deletion can take place only if the relevant surrogate exists in the E relation. Entity references. Entity references can be classified as property references, characteristic references, association references, designation references, subtype references. Property references are references to E relations from their P relations and are governed by the property integrity rule. A characteristic entity qualifies or describes some other superior entity, therefore its existence is dependent on a superior entity which may have multi-valued properties. Reference to a characteristic entity is possible only when its superior entity exists. For example, in the supplier part database, a given order line can exist only if the corresponding order exists. That is, order lines are characteristic entities qualifying orders. Characteristic entities are constrained by the characteristic integrity rule. An association is a many to many, too many, etc. relationship involving two or more independent entities. Associations are themselves considered to be entities with all the consequent possibilities such as properties and surrogate values. When an entity reference is made using such association, entity, surrogates or properties, we call it an association reference. Association entities are considered based on the associative integrity rule. A designation is a many to one relationship involving two independent entities. For example, in the supplier part database, let us make city an additional independent entity for both a supplier and part. Then SC city represents a designation reference to city from supplier, and PC city represents a designation reference to city from part S and P. Therefore, are designative entity types. Designative entities are subject to the designative integrity rule. In an entity supertype, subtype hierarchy or generalization hierarchy, a reference from an E-relation for a subtype to the E-relation for an immediate supertype of that subtype is called a subtype reference. Subtype references are constrained by the subtype integrity rule. Rm given T operations. Rm given T operators, common Rm given T operators such as create, insert, etc. have already been referred to in earlier paragraphs for corresponding functions of entities, properties, and surrogates. Rm given T also offers special operators in addition to standard relational algebraic operators. Denote applied to a relation. Name returns the relation denoted by that name. It also returns a set of relations denoted by a set name. Compress reduces a set of relations to a single relation obtained by repeatedly replacing pairs of relations in the set by a single relation until only one relation is left. Tag tags the tuple of a relation with the name of the relation. Partition R, A is a set of relations obtained by partitioning R in accordance with the set of all distinct values of A. Apply property temp generates a set of P relations for a set of entity types whose names are given in temp. An attribute relation contains a tuple for each attribute of each relation, also indicating whether the primary key and the user key are involved. Rm given T catalog. A catalog structure can be defined by compiling a list of various concepts and definitions in Rm given T. The Rm given T catalog is logically analogous to the concept of a data dictionary. It can act as a conceptual forerunner in any future implementation of Rm given T. Relations are to be identified in the catalog by the surrogates and not by their external names, as the keys are subject to change. However, for simplicity, it may be presumed that the catalog is a collection of internal n-array relations with all the surrogates hidden and without their explicit separation into E and P relations. The Rm given T catalog consists of three relations: domains, relations, and attributes as follows in usual notation. Domains contain a tuple for every domain. Relations contain a tuple for every relation. A relation can be an E relations or P relation. In addition, the Rm given T catalog also contains graph relations whose function is to graphically represent the connection among relations in the database. Example, connection between E and P relations. Conclusion. Rm given T provides a conceptual semantic framework for a regular relational database, while it is only a modeling framework for the database designer. Both the database management system and the user will continue to hold the conventional relational view of the database. Rm given T offers the concepts of entities, properties, and their various interrelationships in terms of associations, which can be expressed as conceptual graphic relationships. All standard conventional relation operators are permitted. In addition, a few operators such as denote, compress, etc. are also defined in Rm given T. The Rm given T catalog is the equivalent of a data directory for all the domains, relations, and attributes. No direct implementation has been reported. Relational versus object-oriented database systems. Relational databases. The relational database model is made up of tables consisting of rows and columns. Each column has a name and a single data type. Multiple dimensions are represented by multiple tables which are joined to construct a multi-dimensional object or by multiple rows in a table. Relational databases support integers, floating point, character strings, date, time, currency. If it doesn't fit any of the above, then it is a BLOB, binary large object-oriented database. An object-oriented database provides for data objects that store in one data structure. The data, rules and ways about how the data looks, acts, how it can be manipulated, and how it can be accessed. Allows for complex data types to be intermingled in one database. Allows for algorithms that let the database search in multiple dimensions. In an OOD environment, developers can create structures that model how the data will be used. An OOD and its database management system DBMS is aware of how to access or extract internal components of an object, for example, 1 or 2 frames of a video, execute operations or functions against objects without exporting them to the client, extract enough about the object to develop an intelligent search plan to optimize performance. For example, the user wants multiple frames of video plus info on actors, royalties and rights. The OODBMS gauges the speed of retrieval for each item and optimizes a retrieval plan using server resources, freezing the client to continue work. Relational versus object-oriented ORDs. Mature, extensively tested, vast amounts of data in this format already. Programmers know how to optimize for high-speed retrieval. OODS. New. Here is a general shortage of experienced quality programmers, lack consensus on standards, definitions, etc. Performance concerns. SDM. SDM, one of the earliest comprehensive and formal semantic models, was the forerunner of many a later model and was also a forerunner of a later implementation in SIM. SDM introduced for the first time many semantic modeling features such as classes and interclass connections, complex attributes of objects and their interrelationships. Significantly, decades ago, SDM offered a few advanced features such as derived attributes, which are now considered to be features offered by the new generation expert database systems. Almost 10 years after the initial definition, SDM was attempted to be implemented in SIM, the last commercial semantic database management system. Originally, SDM, Hammer and MC Leod 1981 was designed with the following specifically declared objectives. Number 1. To serve as a formal specification mechanism for describing the meaning of a database. Number 2. To provide a documentation and interaction medium for database users. Number 3. To provide a high-level semantic-based front-end user interface to a database. Number 4. To serve as a foundation for supporting effective and structured design of databases. SDM specification and constructs. Subdivision 1. Specification. The specification of SDM can be summarized as follows. Subdivision A. A database is a collection of entities that correspond to actual objects in the real-world application environment. Subdivision B. The entities are organized in classes which are non-trivial, meaningful, collections of entities. Subdivision C. The classes can be connected by interclass connections. Subdivision D. Entities and their classes have attributes which describe their characteristics. Derived attributes, values are also possible. Subdivision E. The complex attributes and interclass relations of the basic information can be viewed in different ways, and there are facilities available for expressing them. Subdivision 1. Classes. The SDM database specified by an SDM schema identifies the classes in the database and has the following characteristics. Subdivision A. A class name uniquely identifies the class. Example, employee class. Subdivision B. The class has members, the entities that constitute it homogeneously and at an appropriate level of abstraction. Example, employee class as managers, workers, Ravi Kumar, Rama, Krishna, etc. Subdivision C. An entity could be a name, an object, a concept, an event, or a group of entities. Example, Ravi Kumar, Rama, Krishna, employee. Subdivision D. An optional textual class description describes the meaning and context of the class. The class description will describe the specific nature of the entities that constitute a class and indicate the role and significance in the real world. Subdivision E. A member attribute describes the assets of each member of a class logically connected to one or more entities in the same or a different class. A member attribute also describes each member of a given class. Subdivision F. A class attribute describes a property of a class taken as a whole. Subdivision G. The class is either a base class or a non-base class, depending on whether or not it is defined independently of the other classes. For example, all entities will be subclasses or members of the class things in the real world. A non-base class does not have an independent existence. It will be defined in terms of one or more of the other base classes. In SDM, classes are related by interclass connections. Interclass connections can be either those that allow subclasses of a given class or those that support the grouping of classes. Subclass connections. A subclass S of a class C parent class contains some but not necessarily all the members of C. Subclass connections can be either defined by attributes or user controllable, depending on whether the subclass determination is based on an attribute indicated by other information in the database or whether it is defined by the user. Set operators such as intersection, union, and difference are also defined for subclasses. Interclass connections. The grouping connection. The grouping connection is an interclass connection where the grouping class 6 is defined, whose members are of a higher order entity type than those in the underlying class U. A grouping class is of a higher second order because the members of this class can themselves be viewed as classes whose members belong to U. Multiple interclass connection. As mentioned earlier, each non-base class in an SDM schema has a single interclass connection associated with it. Multiple connections may result in an overtly complex schema and may therefore be avoided. Only a single interclass connection should be declared to the extent possible. Name classes. A name is any string of characters which is the actual value of the entity in the application environment. Example 249, that means 249. Yellow. A name class in SDM is a collection of strings, that is a subclass of built-in class strings consisting of all strings over and above the basic set of alpha numeric characters. Name class is defined by subclass, interclass connection in various ways such as union, intersection, or difference of two other classes or a subclass of another class, etc. Figure illustrates the SDM definition of employee details, entities declared or employee, base class, the name, class definitions, descriptions, and value classes. SDM definition of employee details. Attributes. Each class has an associated collection of attributes. Each attribute has features such as name, value, applicability, description, mandatory, optional, changeable, not changeable, etc. While the name needs to be unique, value is an entity or collection in the database selected from the value class which contains permissible values of the attribute or a class attribute. Description is an optional facility to an attribute, giving the meaning and purpose of the attribute. If the attribute is single valued, then it is a member of the value class. A multi-valued attribute itself defines a class. When the attribute is mandatory, a null value is not allowed. If it is specified as not changeable, no corrections or modifications to the value are possible. Member attribute interrelationships. Member attributes can be related in different ways. Inversion is such a relation where a member attribute A of a class C can be specified as the inverse of a member attribute A2 of C2, which means that the value of A for a member M1 of C consists of those members of C2 whose value of A2 is M1. Member attributes derivation. The essential relationship between any two entities can sometimes be shown as equivalent by using inversion and matching. An attribute whose value can be calculated from other information in the database is also defined in the SDM. Mapping. Mapping is a concatenation of attribute names which allows user interface to the value of an attribute. A mapping is written as a sequence of attribute names separated by delimiters, that is, quotation marks. Example, manager name for class departments. The value of this mapping for each member D of departments is the value of the attribute name of that member O of offices, which is the value manager for D. Attribute inheritance. SDM supports attribute inheritance by subclasses from classes or by entities from other superclasses. An entity may belong to more than one class, permitting more than one class to share members. Attributes can be inherited both from the immediate parent class and also other I classes. SDM Data Definition Language (DDL) provides formal constructs for defining the detailed semantic structure of the database. SDM does not directly support aggregation abstraction. Aggregation can be achieved by simulating it with the help of the attributes and their derived properties. Conclusion. To summarize, SDM was the first to be involved in intricate levels of data definition, semantics, permitting data relativism, that is, multiple perspectives of the same data, derived attributes, attributes inheritance, and various types of interclass connections. In addition to a wide range of constructs when it comes to representing the semantics of the application's environment, SDM offers the database engineer a large variety of options of constructs to choose from. Though many of the concepts in SDM are familiar ones, it refines them to a very detailed level, enabling the widest definitions of semantic structuring possibilities. SDM was the first to bring out a few concepts as derived attributes, which later found their way into more advanced environments like the Postgres. While no direct implementation of SDM was reported, the last commercial semantic database management system, SIM, has claimed to implement primarily the framework of SDM. Semantic database systems. Semantic database models and systems present the early approach to achieve semantic expressiveness by object orientation of a database. SIM of the erstwhile Unisys Corporation, semantic models present a gradual evaluation from simple entity relationship diagram models to full-fledged database management systems. Semantic models were predecessors of later object-oriented models in more than one sense, though the alternative paths of the C++ object-oriented programming approach gave rise to a plethora of object-oriented database management systems such as O2, Object Store, etc. Semantic expressiveness of a database model. One of the fundamental limitations of conventional database models, as hierarchical, network, or relational models, can be identified as their poor semantic expressiveness. This originates mainly from the lack of the concept of an abstract object, an essential requirement for a semantically expressive model, as any real-life database application is essentially made up of objects and the relationships. In the data definition, languages of conventional models, the database design specifies record type, classes, and linkage relationship which define inter-record connections. While the primary purpose of a linkage record is to semantically connect related records. In practice, the linkages indicate the access paths, a physical level detail, and this is against the objective of data management, namely data independence. In the relational model, on the other hand, the inter-record relationships are expressed implicitly via common field values, while hierarchical and network models offer a compromise between the conflicting objects of providing a user-oriented model and the need to support efficient storage and access facilities. The relational model distinctly separates the user-level view of the data and the underlying implementation details, and this leads to greater data independence. The relational model also offers a simpler and appealing user interface to a database, but all the three models cannot present a model of an environment which the database model attempts to represent. These ingredients comprise real-world objects of entities and other relationships. These models also tend to utilize the same simple low-level record-oriented structures to model or represent a fairly complex application environment. These models also fail to distinguish between different kinds of generic relationships among application objects. Such relationships have been identified as aggregation, generalization, specialization, classification, etc. In conventional models, there is no structure to represent these relationships. The very same structure as a network or relation is utilized for describing the objects themselves, the attributes of the objects, the type of an object, or even to relate the types of themselves. Due to lack of an abstract object which can represent itself, it is necessary in these models to explicitly make cross references of related objects by means of their identifiers or keys, and this leads to intricate data manipulation and semantic confusion. The logical design of the database in these instances being closely, inseparably linked with the implementation related issues, the chief factors in design decisions involve implementation, considerations rather than design simplifications, a counter objective of data independence. Normalization in the relational model, aimed to be an aid to design, further inhibits the notion of an abstract object. Normalized schemas tend to be unnatural, and splitting of relations to avoid anomalies may introduce new relations whose rows or tuples do not correspond to objects in the application environment, thereby making the resulting database even harder to use. Semantic integrity constraints are also required to be imposed externally on a conventional database, since no provision exists internally in the database model. Such provisions provide only for supplementary integrity constraints and are only and hoc. They do not integrate all available information in a simple structure. Clearly, conventional models do not aim at capturing the application semantics either at the processing and analysis phase, data modeling stage, or at the representation phase, the database schema design stage. This situation is different in a semantically expressive object-oriented database, as it naturally embodies the semantic structure required to meet the aforementioned objectives. Categories of semantic database models. While all semantic models are based on a specific set of fundamental features comprising object definitions, inter-object relationships, hierarchies, type hierarchies, and object associations, they lend themselves to categorization in a few classes depending on their individual characteristics and areas of emphasis. Semantic database models can be classified into the following groups. Extensions of relational models. RM-given-T is a record-based database model that incorporates a set of semantic constructs in relational database models. A type or a class is represented by a type relation that contains a symbolic unique identifier for every type member or entity. Attributes of type members are represented in a separate n-array relation that relates every unique identifier of a member with a set of values for its properties. The aggregation generalization process in this model is based on the aggregation and generalization semantic primitives. Subtypes are assumed to be partitions between the supertype members. Subtypes are also types themselves and may have their own subtypes. Functional database models. A functional database model views objects, properties of objects, object classification, and inter-object relationship types uniformly and defines them as functions. A zero-argument function defines types of single objects, and a multi-argument function defines relationships among objects. Entity association models. A database is defined as a collection of entities, and in terms of the relationship types among these entities. A diagrammatic technique represents the database schema and contains different sets of nodes and arcs corresponding to the entities and the relationships. However, a relationship itself is not viewed as an entity, and the entity association model is unsuitable to represent the semantics of relationships among relationships. Object-based models. Object-based models have evolved from semantic models, though both semantic and object-based models employ the concepts of objects, inter-object relationships, and object associations. A subtle distinction can be made between them, at least in their chronological order of development. Object-based models such as OSAM star utilize the concept of object more explicitly than their predecessors such as SAM star, which were just semantic models. Semantic association model SAM star. The semantic association model SAM star SU 1983 and later OSAM star, an object-based extension, was developed at the Database Research and Development Center, University of Florida, Gainesville, Florida, by a group headed by Professor SWSU. This model, in contrast to the other models, attempts to serve the modeling purposes of a comprehensive range of applications, namely scientific, statistical, in addition to the conventional business-oriented MIS environment. The following sections present the features of SAMSTAR in brief. SAMSTAR salient features. SAMSTAR concentrates primarily on serving the modeling requirements of scientific statistical databases SSDS, in addition to conventional business-oriented and MIS-related databases. Such SSD applications primarily deal with complex data types such as sets, etc., which are conventionally available in the programming language which interfaces with the database management system. These programming functions are aggregation, data conversion, data modification to suit periodicity, time series analysis. As a long-term solution to reducing the efforts in programming for these features, the programmer requires a database management system with an appropriate data model. SAMSTAR is an attempt in this direction. SAMSTAR can be described in terms of its essential features, especially those that distinguish themselves from others, as follows. Integrated model. Instead of defining a semantic model twice separately for the external model, that is, the integrated community view of the database and the conceptual model, the user's view, as in certain other approaches, SAMSTAR permits defining the database both at the external and the conceptual levels. As a result, the mapping between these two levels of data becomes simpler because they all are represented by the same set of semantic constructs. Relativism. The principle of relativism consists in the accommodation of different semantic interpretation of the same data object used with equal care, thereby allowing an object to be multi-labeled to specify the different categories of semantic properties to which the object belongs. Thus, multiple views of the same data object in different applications can be easily accommodated. Comprehensive coverage. The model fully caters to scientific, statistical, and business application requirements. System life cycle applicability. It lends itself to being effectively used to represent the information request as well as the processing requirements, that is, the information analysis, definition phase, external schema, and the practical schema phase, conceptual schema of the system's life cycle. While a graphical method is used for representing the conceptual schema of the database, a tabular representation called the G relation is used for representing the aspects of design and implementation of a database. SAMSTAR concepts and association constructs. SAMSTAR permits representation of the real-world application environment by means of several interrelated concepts. Concepts can be classified as atomic and non-atomic concepts. An atomic concept is an indivisible, physical, abstract object or event or any data element in the database that the user regards as a fundamental information unit, while the meaning is understood and need not be defined. Example, name, age, data, etc. An atomic concept can be a simple data type such as a set, vector, and time series. A non-atomic concord is a physical object, an abstract thing, or an event whose meaning is described in terms of atomic or non-atomic concepts. The grouping of atomic or non-atomic concepts to describe other non-atomic concepts is called an association. Different types of associations are defined. There are 7 types of associations defined. Membership association M. A set of similar concepts can be grouped together to form a set S which represents an attribute type. A set member Si belongs to S. The membership hierarchy is as shown in figure. Depending on the data type, an operation can be performed on an attribute. Conventional union, intersection, etc. can create or modify sets. Rules can be declared to restrict any one group. Example, only BTech students. Aggregation association. A set of concepts called entity. Occurrences can be grouped together to characterize or define another concept called entity type labeled A as given in figure. Associations are defined on the basis of different structural properties, operational characteristics, and semantic constraints. Structure. Aggregation consists of a set of concepts formed by taking the cross product of a set of concept types XICI where a member belongs to A such that all XICI varying from 1 to n, where n is the number of members which together constitute A and are characterized by attribute types like employee number, EMP number, e-name, age, and salary employment number, is a unique identifier where values uniquely identify occurrences of employee. Each occurrences of employee is a member of the cross product of the attribute types involved. A concept in this association can be an attribute type or an entity type formed by aggregation association, thus involving recursion, or formed by a combination of other associations. Operations: addition, deletion, update, and retrieval of component concepts are the possible operations on occurrences. Insertion and deletion of occurrences should follow existence constraints. That is, the final parent node has to exist and be non-null. The set of occurrences of aggregation is subject to set operations and relational operations or their equivalents, that is, select, join, project, etc. Adding concept types to a set of component concept types is also possible. Constraints. Existence constraints. The existence of entity occurrences depends on the existence of parents in a hierarchy. The root node is the independent entity type, while the child node is the dependent type. Infra-occurrence constraints. Constraints within the occurrences are allowed. Example, no employee salary can be higher than rupees 50,000. Subdivision C. Inter-occurrence constraints. For example, if an employee who earns a salary of rupees 50,000 exists in the database, no other employee earning a salary of rupees 25,000 can exist. Unique identifier. Among the non-atomic concepts that define an empty type, there exists some, usually a single or a group, whose members can uniquely identify the entity, similar to the concept of primary key. Multiple occurrences. For a parent node, multiple occurrences are possible. Example, address during the last 5 years. Generalization association G. Concepts can be grouped together depending on the generic nature to form a more general concept called generic type, and the concept types which form a generic type are grouped together to form the generic occurrences. Set exclusion, set equality, set subset, and set intersection are constraints specifying relationships between two sets in generalization. Interaction association 1. Independent entity types can be grouped together to describe a set of entities or facts which are the result of interactions among the occurrences of these entity types. A named set of facts or events may be called a relationship type, and the events or facts themselves may be called relationship occurrences. Example, the entity type students, course, teacher together forms the relationship type course enrollment. Cross product association. X. Concept types are grouped together to form another concept type, the cross product type, whose occurrences are the result of taking the cross product of occurrences of component concept types. In the example given, the population group defines a set of occurrences which are the result of taking the cross product of a set of occurrences defined by the personal category and the socio-economic category. Operations. At the occurrence level, the update and retrieval of a part of the whole occurrence is allowed. The occurrences of a cross product type can be aggregated or grouped with respect to values of some attribute types to produce another cross product type. The order of the attributes in which occurrences are aggregated can be changed or reordered without changing the semantics of the cross product type. Constraints. Subdivision A. All members of the cross product of component concept types are legitimate occurrences of the cross product type. However, at a given time, the database may not contain all the members of the cross product and can be specified as constraints. Intra and inter occurrences as constraints can be specified. Composition association C. Concepts can be physical parts or functional components that go to form other larger parts or components. These component concepts can be grouped together to define a larger part of another component, the resulting concept being called a composition type. It contains a single occurrence, which is a set of sets of occurrences of component concept types. The set of sets is treated as a single entity at any given time in a database. Composition association. Summarization association S. A set of concepts IC, S1, S2, S, etc. can be grouped together to form another concept called the summary type, where IC is an identifying concept C of type X, whose occurrence identifies a set of objects, and S1, S2, Sn are attributes which summarize or characterize the set. Each occurrence of a summary type specifies a set of objects, and summarization or characterization of the set in terms of 0 or 1 attribute values illustrates what is meant by summarization association. In a census operation, the population of individual states together can be considered to form a summary figure of the national level population. These different types of association are defined on the basis of different structural properties, operational characteristics, and semantic constraints. Summarizational composition association. The architecture of object-oriented databases. Object-oriented database management system architectures and overview. The basic approach of object-oriented database management systems is to extend and implement the objects of object-oriented programming to the database management domain. The application or extension of object-oriented programming concept to a database management environment necessitates the provision of additional characteristics necessary to support storage and manipulation of large shared and persistent objects. These characteristics typical to the database environment include support mechanisms and the indexing schemas for large secondary storage organizations of a database, concurrency, control, and recovery. These database management systems aim at effectively meeting the requirements and the complex demands posed by advanced database applications. The approach of extending object-oriented programming concepts to the database environment is one of the several approaches object data management. The other approaches discussed elsewhere in the book are Subdivision A, the semantic database systems approach. Subdivision B, the relational extension approach. And subdivision C, the database management system generation toolkit approach. We will now survey the various database management system architectures within the domain of extension of object-oriented programming concepts to database management, popularly known as the object-oriented database management system approach. The central theme of a database management system is this approach, in contrast with the conventional database management system, which stores only data, is that an object-oriented database management system stores objects and not data. Objects here imply the definition of objects as in the object-oriented programming paradigm with the encapsulated combinations of data structures together with associated methods or procedures. This allows instances of arbitrary kinds of data to be stored in the database. In contrast with a conventional relational database management system, a typical object-oriented database management system is characterized by at least the following differences. An object-oriented database management system supports user-defined data structures and operations on it as object classes and methods, while a conventional database management system simply restricts the users to instance of a single built-in type, that is relations, and a fixed set of operations on it, that is relational operations. This implies a much greater scope for user-defined database definition and composition, avoiding the constraints otherwise imposed in a conventional database management system. An object-oriented database management system supports the concept of object identity. This means the object as an identity independent of its attribute values, and this identity can be used for referencing the object from within other objects. The identity is generally represented by a system generated unique value or object identity OID. Such object identity is simply absent in a conventional relational database management system. An object-oriented database management system supports direct object relationships, that is, objects related to a given object can be accessed by involving a method of the given object which searches for object identifiers as the related objects in instance variables. Thus, related objects are treated as if they were part of a given object's internal data, rather than requiring a join operation on attributes of the object, while some object-oriented database management systems also support operations similar to joins. They are generally more efficient than simple joins in accessing an object given the object identifiers. Inheritance is another feature supported only by an object-oriented database management system. Advanced object sharing, concurrency, control mechanisms, versioning, and predefined object libraries are also supported. The semantic expressiveness of an object-oriented database model, which is supported by an object-oriented database management system, has already been discussed in Chapter 2 in the context of semantic database systems. In addition, the semantic gap between the objects and the program's methods manipulating if it also reduced. In the context of object-oriented database systems, 3 levels of object orientation of database management system are defined. These are as follows: Dietrich and Davel, 1986. If the data model allows the definition of data structures to represent the entities for objects for any complexity for complex objects, then the model is structurally object-oriented. Semantic database systems and object-oriented programming extensions both satisfy this definition. If the data model permits generic operators to deal with complex objects entirely, instead of requiring them to decompose the operations to simpler operations As in the case of relational tupules, then the model is operationally object-oriented. It is also implied that such models are structurally object-oriented. Once again, both semantic and object-oriented models fall in this category. If the data model, in addition to being structurally and operationally object-oriented, also permits the definition of arbitrarily complex object classes together with a set of operators, so that the object may be used only by calling these operators, the internal structure of the objects may only be accessed by the implementation of these operators. Then the model is behaviorally object-oriented. Models in this class also provide full programming capabilities to permit the definition of object methods or procedures as defined earlier. That is, if the methods are also supported, then it is behaviorally object-oriented. Clearly, only object-oriented models, extensions of object-oriented programming approaches, fall in this class. All other models, including semantic models, do not qualify to be in this category due to the second part of the aforementioned definition, which access only through methods. The categorization is, however, not absolute, since many systems which claimed to be object-oriented do not conform to this. Example, relational extensions as Postgres. In practice, however, as opposed to purely theoretical grounds, the implementation of an object-oriented database management system has been attempted in 4 distinct methodologies. The first is to extend an object-oriented programming language, C++, environment to persistent storage and database management. The second is to follow the semantic database systems approach. The third is to build certain object-oriented features on the top of a relational database management system, which are only operationally object-oriented while not being object-oriented at structural and behavioral levels. The fourth approach is to provide database management system generators with a toolkit assembly facility to generate a tailor-made object-oriented database management system optimized for a given application. Conclusion. In this chapter, we have covered the following in detail: relational versus object-oriented database systems, semantic database systems, object hierarchies, generalization, specialization, aggregation, ER model, RM given T, SDM, SAM, Daplex, IFO, the architecture of object-oriented databases, query languages for object-oriented databases, Gemstone, O2, Orion Object Stone, Object Relational Database, Management System, Object Relational Database Management System, Oracle 8i, 9i, DB2. Overview of Object Database Systems, Object Relational Database Management Systems, implementation and challenges, database design for an Object Relational Database Management System, Object-Oriented Database Management System, a ODMG data model, and ODL. Comparison of Relational Database Management System, Object-Oriented Database Management System, and Object Relational Database Management System.